Mhm. Okay, so sounds like it's been a while since I've done the remote thing, so I have to kind of remember how I had used to have it set up. So generally, I have about first of all, my name is Brian Gamble, and this is physical science, physics one, and welcome to class. Welcome to class. We will be meeting, obviously remotely. We're made to 11. And I have to apologize to you. There was a mistake, actually, I think that was made on the registration. This class should have been completely online. Many of the lectures, most of them already have pre-recorded, but I think there was some sort of scheduling mix-up, and so they scheduled that you have to be in class. Um, so we have to actually meet because that's the way the class is set up. Although the spring class, I think, will be fully online with pre-recorded lectures. But the course really, it's physical science. It's really kind of the book that we have here is a pretty good book. It reads really well, and it's mostly a reading course. But I will go through and kind of highlight things in the chapters, and it's not really that quantitative. It's meaning it's not really a math-based course. It's more a kind of qualitative, and we do have a little arithmetic here and there and things like dimensional analysis. But the course is designed just to make you familiar with science in general and from a physical point of view. And we highlight we kind of focus on physics to some degree, but there's other topics that we cover and kind of touch on, like, for example, I think in this first chapter, they introduced the periodic chart, at least show you what it is, and that's chemistry, it's not physics necessarily. So, but because I am a physicist and because, I kind of maybe lean toward physics, so to speak. But, the course is designed just to be an informative course for those of you who are not necessarily going into science or not scientists or going to be scientists. It just kind of introduces you to the, the study of the physical universe. Um, yeah, so today I would like to, it's kind of an introductory um, class. I have apologized for not publishing the module on Friday. Usually I try to get it before the weekend of the first day, but published it yesterday, so you should be able to see that up. And if there are any issues, let me know. The syllabus is there on the website. In fact, I was going to go through that. Just I was having difficulty pulling it up from my Canvas page for some reason. I think there might have been some issue, but um, can someone? Well, actually, let me see if I can share my page and you can go take a look at the. Hey, can everyone see my? Yeah, we should see the page. So you can access the syllabus a couple of places. One is here under the syllabus page, and I have kind of an introduction to myself and that sort of thing. But here, somehow this link wasn't working a few minutes ago, so let's see if it's working right now. Yeah, so I'm not sure what's going on with that. Hmm. Is anyone else getting that? If you try that page, is that also happening?
the heck? Okay.
If you also go to, let's try another. So if you go to module, in the first module here, yeah. So here on the module 1, there's a syllabus page, and I think I uploaded it there as well. So let's see if that's going to work. Hmm. Hey, what I'm going to do. Why don't we come back to the Zoom page? And I think I can just share it within the chat. Hi, is it?
It's funny because I just got the same pop-up as you did. I got the error screen.
Okay. Yeah, I don't know what's going on with that. I will share it. And Mr. Rabatu, I don't know how you have to help me with your first name when we do introductions, but yeah, the class is only going to be on Zoom. And the lab, basically, there's not. So I know many of you are not taking the lab. It's the lab for this class is Physics 14, and it's not. It's a separate lecture. It's a separate class actually, but it's completely online. Which again, it was just so. I haven't published that module yet, but I will, and uh, that's when there's even no meetings for that. And many of you, I'll talk about it here in a minute, but many of you, the lab is going to be a virtual lab, and I use something called Beyond Labs. And for those of you who are registered in the lab class, the administrative assistant in the department should have emailed you a code. The department actually does pay for it, a code for Beyond Labs. And you should have received that in your inbox somewhere, and that you use that for the registration for Beyond Labs. And we'll talk about that a little bit later on in this class for those of you who might be taking that as well. But if you, yeah, you still sign up for the lab. So yeah, you can still sign up for the lab, Mr. Patterson. Sure. Mrs. Stephanie. Yeah, you can still sign up for the lab. I guess I have to give you a code though. So if you'd like, do me a favor, email me, and whenever you're this is also on the syllabus. But for now that we have a register, well, I guess if you're in the lab, it was on. Yeah. So basically, I would like for you to use the Canvas email for class. You probably get a quicker response from me because as opposed to using the office email. I checked the office email. I don't think too many people use that email to try to contact me prior to class. But at this point, use the Canvas email, this inbox within the class. And because I have notifications on my phone when that happens, and usually I'll respond to the Canvas inbox faster than my office. Yeah, okay. So for the Wiley Plus, I hope you look at the announcement. At this point, we don't have a registration code. The department does not pay for Wiley Plus. And Wiley Plus is the learning management system that I'll be using to manage the class. So if you go back to, I'm going to share this again. So this is basically our Canvas page, the syllabus page as I just mentioned. But on the left-hand menu, you've got the various pages for the Canvas LMS. if you go to this Wiley course resources that I upload here, if you go there, it's going to bring you to a registration page for Wiley Plus. Now, it doesn't for me because I've already registered, but you get a free digital book with that registration, and the book is here. You'll launch it with this Wiley Plus textbook. So once you register, when you click on that link, you're going to get a registration. It actually takes you to Wiley Plus registration within. It's embedded and paired within our Canvas module. So the registration, you have to formally go through a registration there on that page when it comes up. And after you complete that registration, Wiley will send you a code to the email address that you register with which you register. And I have to say that I do require registration because it's the only way I can manage the class remotely. Well, it's the most efficient way. All of the homework and many of the tests and quizzes, I use the Wiley source resources. And so you have to be registered in order to be able to access that. And again, you're accessing just the homework on your LACCD Canvas page, but I have paired a course on Wiley Plus within our Canvas. And so when you click on the homeworks, it takes you to Wiley within our page. And kind of like it just did here. It doesn't really look like you're on the Wiley Plus page, but because it's paired. But all of the homeworks and quizzes, some of the tests are set up that way. So I do require the registration. Now, there's various options you have to register for Wiley Plus. They've actually increased from when I ultimately started using this about 4 or 5 years ago. So I think they have various different options, but I think the cheapest option is like a semester for like $70, something like that. But you can get I guess for you all, since this is just a one semester course, then that's on the cheapest version is really the only one that you would really need. And you get as I said, with that, you get access to all the homeworks, and there's other things that they have there, student resources and practice, I think, material, in addition to being paired with Wiley Plus through your Canvas page and being able to access the homeworks that I've already set up within your LACCD Canvas page. And again, you do get you get a digital book that comes along with the registration. Yeah. So hi, Tomeko. You've already went to the page. Is that what it is? 76. And the book comes free with the purchase. So you verify that? Yes, that email, gamblebk@laccd.edu. It'll be on the syllabus whenever we get it up. Yes. Okay. Thank you, Tomiko. And is there registration? Yeah. So you do have extra. You have to purchase it, and yeah. So let me see if I can go ahead and share the syllabus right now. So there you go. Let's see if you can go ahead and click on that. See if you can access that. The syllabus in the chat menu there. And let me know if you can access that. Maybe Julia, can you access I think you were running before. Can you access the syllabus there in the chat menu, or can you see it? Is it there?
Let me see. Let me try it again here. Where am I at? Hold on a second.
Did not come up. Maybe it didn't come up.
Let's see.
Maybe it didn't. Okay.
It's buffering.
I thought it went through. Maybe it did. Let me try that again. Oh, so I guess it did go through because it's not letting me upload. So can anyone can you see the syllabus there in the chat? No one?
Nope.
Okay. I can see the syllabus on my phone. What does that mean, Tamiko? You mean within the chat, or did you go to the web page and did it download finally on Canvas? Okay, so you're having access on Canvas now. I have it downloaded. Okay, maybe it's working now on Canvas. I'm not sure why it wasn't before. So that's good. I don't know why I didn't share here. Normally just drag it onto the chat and it goes in. Somehow it did something different there, and I'm not sure why. Wow. Okay, let's try it again. Yeah. Oh, there you go. There you go. All right. So now it should be in chat. Does everyone see the syllabus within the chat?
Yes.
Okay. Yeah, I guess read it. Um, Canvas. That's I remember having something. Julia, I think there's some sort of tapping going on. Is that you?
Yeah, I'm moving my mouse.
Oh, I see.
Yeah. Sorry about that.
All right. You know. Uh, okay. Looks like I'm able to share it there now. You have to stay the full 3 hours. Um, well, I'll be having class. Sometimes we will probably leave a little early. Once I'm generally, as you can see from the syllabus there, we're going to do about 15, 16 chapters. I do it's approximately 2 chapters per week. And so this first week we have chapters 1 and 2. Um, it's I can go over this material in less than 3.5 hours for 2 chapters, to be honest with you. I think that so generally, and the labs again, the lab is not really associated with this class. It's a virtual lab, and so that's not something that we need to be in class for. So I honestly generally do find that even with the pre-recorded lectures, they're not 3.5 hours every day. Um, which is one reason why the class should have been completely online as opposed to meetings. But at this point, we will be meeting at 8 o'clock every day, not necessarily going to. I don't think it's going to take us 3.5 hours to cover the material in every class period. So yeah, I'll let that. That's as much as I'll say about that. But as far as attendance, I will be taking roll at least for the through up through the census day. And but honestly, it's designed to be. I've designed the course to be more of a reading course. And as you can see, the homeworks are there, the quizzes are there online. I'll be publishing those probably the Friday before the week opens every day, every week. And you can kind of get ahead. And in fact, I might go ahead and publish week 2. I mean, you have it published a week ahead before you get there, at least by the half the week prior. And you can kind of work ahead. And even if it's not published, we're going to be doing the straight. You see the syllabus area, which is going to be doing chapters in sequential order. So you could go ahead and read ahead if you wanted. The material is pretty straightforward. So um, it's not really even necessary to, unless you have any outstanding questions, uh, to uh, to be there for the full class or have a full class in order to communicate the material. Yeah. Regarding the syllabus, I'll keep it up there. So the grading scale is where we'll be doing. Um, well, actually, um, this, the laboratory again should say here it's separate. It's actually a separate lab grade. So those of you who are not registered for the lab, that is literally a separate grade. So it's not going to factor into your grade here. Um, think that, yeah. So you see here on the grading, there's no, even though I did put it in the syllabus here because we don't meet um, for that class, the laboratory is a separate class. So you're only going to be graded in this class on homeworks, quizzes, tests, and the final exam, and there's a discussion. So uh, not every week. We do have a discussion section this first week, which is kind of introduction. And I will be making up other discussions as we go forward. Generally, with discussion, it's a situation where I give some sort of prompt question, you respond to the question, but then you also have to give you time to read some of your other peers' responses to that prompt and then respond on their page. And you have to do that to get full credit. And then sometimes I'll go in and respond to various students' uh, responses as well. And it's usually some topic about science. Um, like semester I did global warming or just whatever, sometimes relating the science that we're discussing to what's going on in the world, current events or in the world today, but focusing on some aspect of our topic and subject matter that may be relevant relative to the world at large, and just getting your feedback on that. So this shows you the breakdown of the grade distribution. Discussion 5%, quizzes 10%, homeworks 15 tests, and that's the average of all your tests, 40%, and the final exam is 30%. And the general grading scale is kind of standard, 90 to 100A, 80 to 89B, so on and so forth. Yeah, something there about financial aid. So just a standard syllabus. Office meetings, actually, there are scheduled office meetings. I think this is for the spring, so I have to change that. But you can also schedule office hours with me after class. Is usually a good time to talk. But if you have any other time, I can you just set up a meeting, and basically we can do a virtual meeting if you need to. But again, unless there's some sort of personal issue you're having, whatever, the course material really is just, it's not that difficult. It's really just reading. And it's a reading course, really. It's not really a quantitative science course. Not much. And there's a few problems in the homeworks that they have there, but it's usually more description or short answer. And every now and then you might have to do a little bit of arithmetic. I will do some today, I think, just to introduce something called dimensional analysis, which is something that most of you probably already know how to do. You kind of do it in your head, but I want to try to quantify that because they did have it in the chapter. So, and I didn't introduce myself. So let's have an introduction, a formal introduction. And in this, if you would, for those of you who are here, I'd like you to turn on your cameras, and we're going to have a few things that will respond. It will be your name, where you're from, what your major is, and why you're taking physical science. So I'm going to demonstrate and also write my name on the board because I don't think I did that. And can everyone see the board? Okay, I guess this looks like there's plenty of lighting. So my name is Brian Gamble. Brian Keith Gamble, actually. I am, because this is physical science 101, or physical science 1. Only one section. I don't readily remember the section name, but I'll tell you in just a second. The section number, that is. Yeah, we're section 16501. So I'm originally from South Carolina. I've been out here for about 20 years. I've been teaching physics at the college university level. In a couple of years, I taught math in a high school, Brad Charter High School. It's been maybe 26 years, 26, 27 years. I am originally from the South. I grew up in South Carolina. Was every now and then you can hear a little twang in my voice. I went to undergraduate at a military college, the Citadel, the military college of South Carolina. Then worked a couple of years, went back to, got my master's in physics at North Carolina State University. for Wolfpack. Taught for a few more years at a small um, it's a small community. Well, it was a branch campus of the University of South Carolina, but while I was there, it broke away and became an independent small university, Coastal Carolina University down in Myrtle Beach, South Carolina. Taught there for a few years, and then went back to Clemson to get my PhD in physics. And yeah, so I've been did research for a little while. Was fortunate enough to spend a couple years at Los Alamos Labs out in New Mexico, and that was a really interesting experience. The last 2 years of my PhD program. So I did some research then for a while, but ultimately decided to go back into teaching. And I've been teaching now, as I said, for quite a few years. And I've moved out here to LA in 2020, in 2004. So it's been 20 years I've been out here, and I enjoy it. So I was, I'm one of those kids. I was 5 years old when we went to the moon. I literally remember my mom getting out of the bed. It was 1969. Yeah, man, it was a mind blower. Getting me out of bed and watching the whole, one small step for man thing, and I, from that point on, was just fascinated with science. I wanted to be an astronaut, so I went to military college. Never quite made it to NASA, but now uh, with space travel becoming privatized, I still might have a shot at it. I don't know, but I ultimately did, just as I mentioned, studied physics, and I'm just fascinated with the study of the physical universe. There's so much to learn, and every mountaintop we climb, we see there's more vistas to conquer and to know. And yeah, so I became a scientist. Um, yeah, so that's me. So if you would, I'm going to go through and you can tell me what. So again, name, where you're from, your major, and also why you are taking physics, physical science, and just what you plan to do, in your careers or whatever. So I'll just start. Julia, how are you?
Hi, I'm good. How are you?
I'm good.
So, my major is elementary education. I'm taking this class solely for the prerequisite.
Okay.
And I'm pretty new to this class, so I'm excited. I'm eager to learn. Yeah,
Good. Good.
yeah.
Well, I have to say, uh, I'm a child of educators. My mother was a second grade teacher for 35 years. And
Wow.
yeah, so and my sister is she's early childhood development. She got her master's there, and she's been teaching now
Mm-hmm.
longer than I've been teaching actually at this point. And my parents, they're actually still with us. They're in their 90s and retired. My father started off as a history teacher and ended up,
Wow.
you know, uh, superintendent of one of the. He worked at the State Department in South Carolina and was superintendent for about 10 years in one of the districts in South. So he went all the way. So I know
Wow.
all about that education, and I was, was your mom a teacher, or did
No,
you?
my mother's a dental hygienist, actually.
Oh, really? Wow.
Yeah. And my dad,
So,
he works for like the studio, so like he makes like television, like the commercials and stuff.
yeah.
So
Oh,
he's
good.
all into the movie industry as well. And he was a child actor. So I don't know if you're familiar with the movie The Bad News Bears.
Yeah.
He played as Miguel.
Oh, really?
Yeah,
Oh,
that's my
wow.
yeah.
That is awesome. That is awesome. Well, uh, yeah. I mean, it's LA, right? So got a lot
Yeah.
of people in the industry. That's really wonderful. So he's producing now.
Mm-hmm.
That's cool. That's cool. Yeah, he has a production company. Does commercials or
Yeah, he does
director.
public transportation.
Oh, good.
Yeah.
That's awesome.
Yeah. Yeah.
Oh, your PC doesn't have a webcam. Okay, no worries. It's all good. It's all good. Just reading the messages. Well, welcome to class, Julia,
Thank you.
and
Thank you.
it's great to have you. And yeah, glad you chose this as your prerequisite for your education requirement.
Hmm.
Um, is it Silly? Silly Buns? Cilie? How do you pronounce
Oh,
that?
Soleil.
Soleil. Soleil.
Yes.
Hi, Soleil. How are you?
Oh, I'm good. How are you?
I'm well. Uh, yeah, go for it.
Yeah, my name's Soleil. I'm from Los Angeles, born and raised, and I'm majoring in English. And the reason I'm taking this class is because it's a transfer requirement.
Okay. Well, English. Are you gonna write, teach, what?
No, I want to be a lawyer.
Oh,
Oh.
pre-law.
Yes.
Okay. Do you know what type of law you're gonna practice? You're gonna wait to decide that.
Corporate law. I want
Oh,
to. Yeah.
okay. Well, that's wonderful. And yeah, I know a bunch of lawyers, but I know nothing about the law other than, just
Not to
what
break it.
that's right. Other than not to break it. Um, well, yeah, I'm glad you chose this class, and there's some benefit here. The kind of quantitative thinking. It's interesting. I was a while back. Of course, I have to do jury duty every now and then, and at one point, I did have to sit on a trial, and it was so interesting to me to see how people don't know the difference. Many people don't know the difference between a fact and an opinion,
Hmm.
and how that can be swayed, when it comes to debate, and particularly with the law and that sort of thing. So maybe one thing that people that you could take away from this course is kind of the objectivity. Talk about that actually in the first chapter, the scientific method. There's five, depending on how people explain it, maybe six, 5 to 7 different kind of categories and modes of the process of solving problems. That's what physicists are, solve problem solvers. And when you solve a problem, you have to have a certain set of criteria, facts, and information about a system. And you once you have that information, then you kind of have to think about it, manipulate it in such a way, that you get some sort of understanding. So basically, just objective and higher order thinking is
Hmm.
what scientists do, and I think it helps. Taking some kind of science course, it can help with that kind of logic and decision making and being able to determine and suss out fact from opinion or fact from non facts. Um, so I hope you get something out of the course and welcome to class.
Thank you.
Yep. Uh, Tamika, how are you?
Hi, I'm doing fine. My name is Tamiko. My major is psychology with a focus in either forensics or research. I'm taking this class because it's a prereq, but I am interested in science in general, so I will.
Okay. So forensics, that's like police work and stuff like that. Huh?
Yeah, so what I want to do is with that is to, actually s- talk to the actual people in jail to, figure out the things that they did and in that nature. So like true crime in a sense.
Okay, well, that's intense. How did you get interested in that?
Well, just basically watching like the true crime documentaries and everything else. It's just fascinating to me to learn about like people's thought processes and like how they do the things that they do and the
Yeah.
reason behind it. So I always
It
have
is.
to know.
It is fascinating, quite fascinating. And again, it's problems. You have a set of evidence, try to figure out, piece together a story. You see these people do that. So it's so fascinating watching these people do that on these shows, like CSI and that sort of thing. Well, welcome to class. Um, Caitlin Orozco.
Yes, hello.
Hey.
My name is Caitlin Orozco, and my major is engineering. The reason why I wanted to take this class is to transfer, and also because I'm interested in science,
Ooh, what type of engineering?
robotics.
Oh wow, that's a very interesting field. With all the so I guess are you into AI and all that? GP, have you started to play around with was it GPT? What is it called? GPT? I haven't done it yet.
ChatGPT.
Chat GPT,
Yes.
yeah. Yeah,
Mhm.
cool. Well, yeah, it's changing the world. I mean, I don't need to say much about that. But certainly robotics, quite interesting field from what I understand. And how far are you into it? Have you taken any courses? Have you made a robot yet? Are you one of those people that do those, what is, make those robots to go fight and stuff? Those things. You fight the robots.
I
You ever
haven't
done
yet,
that?
but I'm actually like interested in like trying to like see if there's any classes for it.
Yeah, cool. Well, yeah. Well, welcome to class, and hope you get something. So why are you so engineering? So why are you taking this course? This is generally people take this. Is it like a prerequisite? Is this like your first science course or something, or like
This
generally
is
you?
my first this is like for a prerequisite for a transfer, but the reason why I'm also interested in science is because I want to know how things are like made. Also, I've been interested in molecule structures and atoms and like how things are made. And I also like cosmetology and science and astronauts. I also like space.
Same.
I see. Well, let me rephrase the question. So, with many of the engineers, it's a different. So, in physics, we kind of have a couple different strands of or pathways, and so the calculus-based physics is usually, also teach that physics 37, 38, 39 series within LACCD are usually that. So, a lot of the engineering and science majors take that path. So like physics 37 as opposed to physical science. So I was just wondering, are you going to be taking those courses or that start that path as well at some point? Or
Yes.
yeah. Okay. Well, yeah. Well, hopefully I'll see you then. If you end up taking me with that. Is this your base school or LA Southwest, or are you based at another school?
I'm from another school.
Okay. All right. Well, welcome. Welcome to class.
Thank you.
Stephanie. Yeah, Patterson.
Good morning. My name is Stephanie Patterson. Uh, my major is health and related sciences, which is biology.
Okay. You're from LA.
Yes, I'm from LA.
Okay. And you plan to I'm sorry. What do you did you say your major? You did just say your
Yes,
major,
it's
but
health and related sciences, which is biology.
okay. So you're gonna go in the health field?
Yes, registered nursing.
Oh, awesome. Be a nurse. Well, that's awesome. Uh, you know, very much appreciate nurses as we saw during the COVID situation. And yeah, we get a lot of usually get a lot of nurses taking this course. So welcome to class.
Thank you.
And Geneva, is that the way you pronounce it? Geneva uh, Bachelor's?
Hello, good morning, everyone. Yes, my name is Genevieve Batris. I'm sorry, right now my daughter, she stayed home from school. She got a fever, so oh my gosh, I'm sorry. But yes,
Sure.
usually I'm always gonna be like focused and camera on and everything like that. But yeah, so right now, I plan to transfer. Yeah, and I need to know a little bit of everything for my major at the university that I'm transferring to, which is liberal studies. So that is why I fell into this class. And yeah, I do hope to learn a lot of different things. Usually, I don't really know much about, so I'm glad that I'm in this class to learn more things.
Well,
Okay.
well, this she sounds so cute. This is definitely an introductory course in that way, and so it is that kind of course that they kind of introduce you to science in general, without too much rigor of quantitative math and that sort of stuff. And And it's a great, and again, it's a good read. This book, I chose this book because it's really good book. It reads really well, and so I hope that you enjoy that, and as you go through and read and do the homeworks and that sort of thing. So it looks like I thought there were more people, but it looks like people left. So okay, that's cool. I think that's everybody. That's unless like there's just one page up right now, so maybe people didn't want to do the introduction, they left. I don't know. Anyway, um, yeah. So I'm gonna go ahead and just go through a few things that I wanted to talk about, and at least for the first chapter, kind of get us through basically the first chapter, and then I may just let you go since we got another day to do here. And again, only about 2 chapters a week. I think that's more than that is a bit much, and I know that, yeah. So I'm trying to kind of match with the basically with the 16-week course as well. Basically, for 16 weeks, we just do 1 chapter a week. Is kind of the pace that I've been going, and so it's kind of unfair to have you do something different than that. Anyway, that's kind of the way it goes. So, just for this first chapter, the basic things that they touch on are the scientific method, which they kind of go over in the various sections. They say something about they don't call it that, but dimensional analysis. And then it's just, they just go through and talk about funding. It's just kind of an introductory chapter. They talk about funding and science and different things. And they also mentioned the national labs there on one page, which, as I mentioned to you, I studied at one of them at Los Alamos lab. For those of you who don't know, Los Alamos, I don't know if you saw the movie this summer. With about the making of the atom bomb. But Los Alamos Labs is up in the Jemez Mountains in New Mexico, and it's where they built the atom bomb. They did that obviously in the 40s. But once the war was over, it basically, I think Los Alamos might have been the first national laboratory. But then there's all kinds, Argonne. You got the one in Pasadena. What is it? Jet Propulsion Laboratories, JPL. And they're all over the country. Oak Ridge, got a couple of friends over there in Tennessee. NASA technically is one, but it's focused on space travel. They're all over the place, and some of them you don't know about. Even the ones that are associated with the military, like the others in New Mexico. What is it? Area 51
Mhm.
and Sandia Labs. There's several. New Mexico is full of national laboratories, at least 3 or 4 different ones, in addition to the Air Force Base there. Some of you've heard about, some of you haven't. So, very interesting places, the National Lab. And it was a wonderful experience for me working there and just kind of all things that we are doing. The scientific method. So, now, in your book, when they go through this, they don't really kind of quantify it as specifically as I'm going to do here. And if you find it quantified in some way, it might see it slightly different depending on where you look it up. But as I said, there's generally anywhere from 5 to 7 specific kind of processes that are associated with the scientific method. And these processes really are just outlining the way that one is thinking about a process. In other words, I don't know if you know the term metacognition. Now, cognition means thinking, just thinking about a problem. I'll just say in general thinking. But the term metacognition, I think it's hyphenated, maybe not. I don't remember. Metacognition means that you're actually becoming self-aware of your thought process. So you're thinking about your thinking, right? So essentially thinking about how you think, how you approach a problem. Now, when you get into science, what you realize is that it's extremely important to understand how you're thinking, because how you are thinking about a problem indicates your very specific perspective by which you are looking at that problem. And perspective is huge. Perspective um, can really shade how you are interpreting your environment. For example, I have a little story that I made up that illustrates this perspective. So, this poet is one day he decides to get up and he goes for a walk, and he sees a really nice hill, and he sits on the hill, and maybe he got up before sunrise, and so he sits on the hill to watch the sunrise, and it's so inspiring to him that he's inspired to write a poem, and he's so fascinated he stays out there for hours, maybe all day, almost half a day, just watching the sunrise and nature, out in nature, and writes this beautiful poem. So then later on that evening, he goes into a bar and he's talking to someone that he meets about how what a wonderful day he has, and he starts to share his poem. And uh, an astronaut is eavesdropping beside him, right, and is kind of listening to the conversation. And then the astronaut decides to come up and she says, well, that's really nice, but all that's it's a fabrication. So it's really not true. Like you're saying these things are really inspiring, and maybe they are, but they're based on something that's not true. You just sat there. I heard you talk about how the sun rose in the east and set in the west and sets in the west, but that's really not true. Because every time I go out in space, I see that it's not rising or setting. We're actually revolving around, around the sun. So none of that's really happening. And but then there's a alien that's sitting maybe a few chairs down and listening to the astronaut, talk to the poet. So the ET comes up and says, "Hey, well, I actually that's not true. Your sun doesn't, your Earth doesn't. You say your Earth revolves around the sun, and it does, but I'm a galactic traveler, and your sun is on the edge of your strand of your solar system, the Milky Way, and I don't know. Maybe he says something like I don't know. But it just goes on from there, right? And so the point of view is that the poet doesn't know anything about that, maybe. So does that invalidate the inspiration, the truth that this poet saw? And it's because, maybe he writes the poem and the poem goes to inspire someone to, I don't know, do what are beautiful things. You know where I'm going with this. So ultimately, what determines what's truth is what a person believes, what you perceive. Right. And so does that invalidate it just because someone else has a different truth that also has validity? So in fact, perspective is actually one of the themes of the course that I teach through all my courses. There's 4 basic themes that I have that I talk about. One of them is perspective. But also technique. That is in technique of. There's actually a technique to applying physical laws. Just like technique in anything, technique in playing a piano, technique in being an athlete. There's technique in the way that you apply, physical principles and for problem solving. And I kind of associate that. We won't do that in this class, but I have a kind of something I call the PPST, which is a physics problem solving technique, which helps people solve problems. Perspective, technique, specificity, someone told me a long time ago, the question that you ask dictates the answer that you get. So you better make sure you ask the right question and make it as specific as possible. Um, about to forget the fourth one: perspective, technique, specificity, and symmetry. Symmetry. So symmetry. Now you may have an idea what symmetry is in geometry. Like if you have a circle or a square or something like that, same, and folded in half. One side mimics the other. Uh, that is symmetry, but that's a very kind of basic understanding of symmetry. When I'm using this term symmetry, what we find in the universe is that the universe is symmetric, and I don't mean just geometrically. I mean that we see these kinds of relationships or patterns in the universe that kind of repeat themselves in various things, and it's a property of the universe that geometric symmetry, obviously, but also this symmetry manifests itself in different ways. It's kind of like, okay, this is what I mean. So I don't smoke or vape, but if I did, and people have seen, you've seen people smoking and vaping. Let's say that you're in a room and there's molecules in the room, oxygen, nitrogen, whatever. But whatever the molecules are in smoke, maybe it's just I don't know what it is. Somebody smoking a cigarette. You've seen someone blow a smoke out, and then you can see the smoke diffuse throughout the room. Well, you can't really see the air molecules. You can see the smoke molecules, but they're interacting with one another, bumping into one another. But gradually, the smoke particles dissipate. In science, we can analyze that, and we can show that there's a classical equation called the diffusion equation, which comes from something something called a differential equation that mathematicians know how to create and then find a solution for. And if we find the solution to that equation, we can actually determine how long, what shape that smoke cloud will, basically how it will diffuse. And these kinds of equations are how you would use that equation, for example, to write a computer program if you wanted to simulate smoke in a cartoon and make it look real, right? That's how they make simulations, right? You have a mathematical function that defines some physical situation, and then you can program that mathematical function, and that's what these basically sci-fi movies, that's how they do it, right? So the symmetry, the reason I'm bringing that example up is because the diffusion equation in that example is associated with smoke particles diffusing amongst other smoke particles in a room. As it turns out, money diffuses the same way in economic systems. So, for example, for a long time, we had an embargo against Cuba because Cuba was, there was Kennedy and Castro had issues. I think now we're actually starting to do business. I think a few years ago, I think we started again. But the point is, for a long time, the capital associated with Cuba was not a part of the United States economic system. If you were to be able to, once we started to do business with Cuba again, if you were to somehow be able to track the actual dollars, the literal money that is now being infused into our economy from Cuba, what you would find is that once it starts, that money diffuses itself in our economic system by the same mathematical equation as smoke particles diffuse in a room. Now, you wouldn't necessarily associate those two types of physical systems, smoke particles diffusing or money diffusing in some economic system. Turns out the physical parameters are analogous. So now the equation won't be it's the same type of equation, but there are parameters that would be different that define is what we call parameters or initial conditions or whatever associated with that mathematical system. But it's the same type of equation, the diffusion equation that ultimately you would have to solve in order to figure that out. So that's what I mean by that. So that is a symmetry. It's where the same type of mathematical function defines systems or describes systems that you wouldn't necessarily think have anything to do with one another in terms of the way that they operate. And they don't necessarily have anything to do with one another directly, but the way that they behave within their own kind of properties is analogous. And so, therefore, you would have the same type of mathematical equation that would define. And so that's when I'm saying symmetry, that's really what I'm talking about. When we look out into the universe and we see how galaxies interact, it might be the same in a way gas, or very similar to way, because it is gas. Gas is interacting, making a star. We might be able to simulate something or simulate that, or actually see various similarities with systems that have nothing to do with galaxies out in space somewhere. And so that's a nice way of looking at the universe. Yeah. So these are my four, and this is something that I've kind of come up with in my teaching, but I call these themes that reoccur within my teaching that I try to point out as a way of understanding. Actually, is that the way you spell themes? There's an A in it. Yeah, it is actually. Anyway, yeah. So, but I was going to describe the 7 steps of the scientific method. Let me do that real quick, and then I'm gonna move on to something else. But first, so metacognition then is, just to finish that up, is thinking about how you're thinking, because it's important. Because I kind of associated that with perspective. Because again, that analogy that I made, if you're just very limited in your perspective, certain perspectives only yield certain properties associated with a system. But if you shift your perspective, you might see things that you didn't see from the initial perspective. And I think, we could talk about that all day long, but you see that kind of thing happening in, in arguments, duality, in politics, whatever, all kinds of things. So I think it's important to kind of have an open mind, because uh, uh, perspectives can show you aspects of the world that you just never thought existed, because it just never occurred from the point of view from which you're looking. So, one of the first steps associated with the scientific method is forming a hypothesis. A hypothesis is basically a guess. You might say educated guess. Well, I don't know how educated, maybe. I like the term empirical. I know that's kind of a classic. If you've back in middle school, when you first heard the term hypothesis, that's what they said, educated guess. I like to call it more like an empirical guess. Empirical is a word that means by observation. So when you look at something for a long time and you kind of become familiar with it, you understand it empirically. You understand it by empirical literally means by observation. And you know that if you're around something for a long time and you look at it and you begin to, you may not understand everything about it, but you certainly begin to understand certain things about it, and you can form guesses about how it's, why it behaves that way, or maybe how it's constructed, or just what the various properties are. So once you make that hypothesis, that empirical guess, then you need to start to test it, right? You try to form experimental techniques to be able to test whether or not that how true your empirical guess is. So experimentation, hypothesis. So you develop experiments, tests, to test whether or not your hypothesis is how close it is. So that's step 2 is another part of the scientific method. Well, once you start to test, data will be created. So you have to figure out how to collect the data. Yeah, that's pretty straightforward. But then you have to analyze the data in various ways. Analyze it for correctness. Basically, are you actually testing what you think you're testing? Um, uh, if you are actually getting data that indicates what you think you're testing, is there some theoretical value that you're trying to ascertain? Um, how close are you to that theoretical value? Or what about the various tests? If you perform experiments and you're doing subsequent tests, how close are the various tests results to one another? So there's a couple ways you can analyze that. You can analyze it relative to some theoretical limit or some theoretical value, or you can analyze the test results relative to themselves. And there's different ways of testing that. Sometimes I'll put this in a little subcategory. So you can percent error. Actually, let's put that over here. Percent error basically compares to a theoretical value. So comparison to an absolute. For example, many of you may know that when objects drop, it doesn't matter how, and we'll talk about this a little bit, maybe next chapter. If this were a vacuum, actually, let me ask you, as many of you may not know this. Let's say that I have a penny, and which I don't know, it's probably just a few grams, and something much more massive, like I don't know, I've got like a steel. Actually, you know what? I've got a 2.5 pound weight over here, which clearly is much more massive. So I've got a penny right here. You can see it in my hand. And I've got like a little weight that's about 2.5 pounds. Now, I want to ask you something. If I drop these things from the same height at the same time, which one will hit the ground first? So, like if I were to, let's see if I can do that. I got a table. It's probably going to knock my table out, or a stand. And I'm just kind of estimating here, right? And it's gonna, but I'm kind of pretty much at the same height. I'm gonna drop them at the same time. Now, the force of gravity. So let me just and I forgot how to pronounce your name, but I'm gonna give it a shot. Soleil, Soleil, Soleil. Are you there? Or maybe she had to step away. Uh, what about Stephanie? Are you there?
Yeah, I'm here. I'm here.
Okay. So Stephanie, 2.5 pounds and a few grams, dropping from the same height at the same time. And clearly, which one is heavier, Stephanie? Meaning heavier, weight is the force of gravity on an object. So if this thing has more, if it's 2.5 pounds, then obviously which one has a larger force of gravity acting on it?
The 2.5 pounds.
Yeah. Now, gravity makes things fall. They will fall at a certain, when something is falling, when I drop these things, their initial velocity will be zero because they're not moving right now. So the instant that I let them go, technically in that very small instant, their velocity is still zero. And then because gravity has a force on them, they start to move and they speed up as they move. So the speed is changing every, you know, increment of time, just like when you press your accelerator in your car from a stoplight, you start to speed up until you kind of ease back on the accelerator and then you move at a constant velocity. But if you were to keep your foot on the accelerator, you would continue going faster and faster and faster. Well, that's what happens when what gravity makes things do. It continues to. If it were in a vacuum, now there's something called terminal velocity or terminal speed, which happens because the air molecules keep the thing from actually speeding more. And on the when you're driving in your car on the road, it's the friction of the road that's actually, and also air drag as well, that is keeping it from continuing. But if it were in a vacuum, it would just, like if you were out in space somewhere and you press the accelerator, you would just keep going faster and faster and faster until you stop with the accelerator. Anyway, so that's what's going to happen. When I drop these objects, they're going to start to speed up and continue to speed up as they move down. So the question is, if one is heavier than the other, which means that the force of gravity is greater on one than the other, which one hits the ground first? Anybody?
The weight.
So was
Because
that
because it's more dense than the penny, so the penny is a little bit lighter. But with the weight, it would drop more because if it's,
all right? So Julia says the weight hits first. That's what I'm assuming. Genevieve?
Well, I don't know. I was just wanted to show like my perspective on this thing.
All right.
Okay, so I think that the penny might be a little faster because you know how skinny people are faster. So I'm like, okay, a skinny person is really, really faster than a bigger person. So that's my perspective on it.
Okay. All right. Awesome.
Yeah, I think the penny
Appreciate
as well.
All right. Stephanie says the penny. And Caitlin, go for it.
Okay, so I don't know why, but I was thinking like, well, I know that like maybe it's the penny, maybe it's the weight. I thought of like maybe it's like at the same time.
Why? Why you say the same time?
I say at the same time is because like no matter like what the weight, like they're both gonna reach at the limit at the same time. So I'm just guessing like they're both gonna like reach the bottom and hit the floor at the same time. I'm just
Okay.
guessing. I could be
Okay.
wrong.
Okay. Awesome. Awesome. So that's very unique. Tamiko, what do you say?
At first I was gonna say the penny because it's lighter, so the gravity is easier pulling it down easier than the weight. But hearing Caitlin say both of them at the same time, it's kind of it could be possible, but I just not too sure. So I'll say
Okay.
the penny.
All right. All right. All right. Well, let's do the experiment. And again, this is illustrating exactly the scientific method. We had an hypothesis, right? And you, even though I haven't done it, you've seen things drop, right? So you're kind of, your empirical guess is from watching other types of systems. And I think it was maybe Stephanie, I think, talked about, well, maybe it was whoever talked about skinny people, and running faster or whatever. And then Stephanie said something about it smaller, whatever. So, this is all empirical, right? Because you've seen things falling, you've seen things accelerating. And so these are the observations that you've had in your everyday life, and you're trying to apply that, again, thank you for using perspective, to something new that maybe you haven't specifically thought about, but it's somehow related. Okay, so now the simple experiment that we're going to create is we're going to drop the stuff. We're going to do it a couple times and see what happens. All right, so same height, ready? And you can see and hear. Woo, pretty big. So what was the result?
Same time it looked like to me.
Stephanie says same time. Caitlin? You're the only one that says same time. What do you think about that? That look like maybe you're
I
right?
think it's the same time.
Yeah. Anyone else? Anyone other? Genevieve or
Yeah, it was
Julia?
the same around the same time.
I was gonna say the same time too, but since I went back to the first option, I think the weight, like I mentioned earlier, was more dense, so it created more of like a bounce to it as you dropped it at the same time.
It's definitely more dense. It made all the sound and everything. That energy came from that. But it's really interesting that so much more massive and heavier. And again, mass and weight are not the same thing. We'll talk about that next chapter.
Okay.
But yeah, it's interesting that because it seemed you know there may have been some human error because maybe I didn't quite drop it the same time, and maybe it's a little bit off in terms of the height. But you would think that because this thing is so much more massive, that even if I was uh, had some discrepancy in the time in which I dropped it and the height in which they were, it seemed like this would make up the difference much more because it's so much more massive. Like, it's I have no, I mean, I'm not really good at doing numbers in that way. But if this thing is two pounds and this is like, maybe a few grams, I mean, this thing is probably like hundreds of thousands of times, definitely tens of thousands, but maybe even hundreds of thousands of times more massive than this guy. So you would think that the force, that it would excel if the difference in mass made a difference in the way gravity attracted it, that it would whatever discrepancy I had with height and time of dropping it, the weight would more than compensate. It would be much less than the margin of error than this object force. So that suggests that maybe Caitlin is correct. And so from that point, what I would do is continue. I'm not going to drop it again because it's so loud and everything, but maybe drop it from a different height, go like, in fact, Galileo was famous for this, dropping objects from the Leaning Tower of Pisa. I don't know if you've read about that or heard about that, but he did this experiment 2,000 years ago with different objects. He just did it over and over again, dropping them from the Leaning Tower of Pisa. And as it turns out, no matter what he chose, they all fell at the same time, no matter what the difference in the mass. So the point is that if I had a Mack truck and I dropped it from the roof of my apartment building and I had a feather, and if somehow I could create a vacuum where air resistance and drag was not a factor, a Mack truck and a feather, they would fall at the same rate of acceleration. Now, the reason for that, and Caitlin, you were the only one who made an attempt at trying to determine why, it wasn't until Isaac Newton came along, and maybe you've heard of Isaac Newton, and introduced his 3 laws of motion. It was only until we had those laws of motion could we actually quantify and specifically explain why that is the case. And so Galileo determined that 400 BC or something like that. I don't know, whenever he was Greek, maybe it was 1000 BC. Yeah, maybe. Yeah, 400 was the Roman, so in Egypt. So I think Greek was like as early as so that's like 3,000 years ago. So we determined that we've at least known in the modern era, maybe even before that, but at least in the modern era, for 3,000 years approximately, that objects close to the surface of the Earth fall at the same rate of acceleration. But it wasn't until a couple hundred years ago, as far as we know, that Isaac Newton had to come up with the laws of motion to explain why it is. It is very simple. It's because the ratio of the mass per relative to the weight. And again, mass is the amount of, there's a lot of ways we can define it. You can define it with density. It's amount of matter in a certain space, and that's basically density. Density or mass density is mass per unit volume. So the amount of matter that you can squish into a certain volume of space is technically defined as density. And that matter we can talk about in terms of, you can also describe it as mass. The first law, Newton's first law, also gives us an opportunity to really define mass in a way that is helpful for physics, because that terminology, the amount of matter contained in space, is really I guess comes from chemistry or biology, a couple different ones. the amount of something that. So I think the first definition of mass that I had was biology, and then like eighth grade or earth science. It was something like something that has volume and takes up space. Anyone remember a definition like that? Does that sound familiar? Somebody?
Yeah.
No. Something like that. I think that was my eighth grade earth science book. Then when I got to high school, chemistry, uh, they defined matter as the amount of substance. What is it? What was it? Yeah, I'm kind of drawing a blank, but basically it had to do with the amount of material within the volume of a substance or something like that. It's interesting that when we get to Newton's second law, Newton's first law, because actually Newton's second law actually defines, well, why, tells us why an object falls at the same, two different objects of different mass fall at the same rate. But and it's called the force law. But Isaac Newton's first law is called the law of inertia. And he defines something called inertia, which is very much associated with mass. And so those two definitions, the one for biology and the one for chemistry, don't really help us in physics. They don't really, and again, this is about perspective. It's not that they're wrong, it's just that they're written from the point of view of thinking about with biology, muscles and stuff involved in the volume of and then from chemistry, the substance of the material, and different substances create different properties on a chemical level. So those definitions are from that perspective. And they don't say anything about the behavior of an object when you have an external force on it, which is what's happening when these objects are falling. We're not worried about the chemistry, and we don't really, just for the most part, we don't really care the shape of them. We will eventually in physics, but we're treating them as something that we call point particles, right? Assuming that the force of gravity is acting on them from their center of mass, something that we'll define later as well. So we need to then define mass in a way that helps us understand what's happening with their falling. And so that's what the first law does. And so again, it's really, I hope, illustrating that it's not that these things are wrong. It's just that perspective makes a huge difference. It can, it's the difference in taking a picture with an X-ray and taking a picture with a visible light. Right? It's still light. It's both light. Visible light is something called an electromagnetic wave, and X-ray is an electromagnetic wave, but they have different properties that affect the environment in different ways, such that if our eyes were X-ray, saw with an X-ray, clearly our whole world would look very different than it looks now. Or if we had infrared vision, and you've seen it in the movies, when you the night goggles and stuff. That's what night vision does, is infrared. So what if our eyes were only, but what if we were beings that had all three? We could see with X-rays, visible light. I mean, it just changes. It's like a different world. So that's how different perspective is. So I've digressed again, but we will talk about why that, and I'll leave it for now, that to really talk about why all objects, no matter what their mass is, falls at the same rate of acceleration. And acceleration is change in velocity per unit time, and why they fall at the same rate when they are close to the Earth. When we're in English units, that rate of acceleration is 32 feet per second squared, and the symbol that we use to define that is something called g, acceleration due to gravity. Its value is 32 feet per second, approximately 32 feet per second squared. But in metric units, it's 9.81 meters per second squared. Acceleration due to gravity. And as I was about to finish up here, so we can talking about comparing and analyzing data, so that's what I was leading to, is that you can compare something to an absolute value. So we know that the acceleration due to gravity is exactly 9.81 meters per second squared. So whenever we're taking these measurements, we can compare, kind of calculate what their acceleration was, and we can compare it to the absolute value that we know is the theoretical limit of what the acceleration is. Or we could take both of these and calculate their various accelerations and compare them to one another. Now, they're not going to be 9.81, but they might be close, but we could see how close they are to one another. And that's called percent difference, where you're comparing experimental values to one another. So at percent error compares an experimental value to a theoretical value, but a percent difference compares a experimental value to another experimental value. A really good way of thinking about these two different types of way of analyzing data is, let's say that I had I was playing darts. Now we can say that the bullseye, the center, is like the absolute, the theoretical value, the theoretical absolute value. Okay, it's the center. Now let's say that, and I think I'm out of color. Where are my colors here? Yeah, I think took all my markers to school since I wasn't teaching from home anymore. No, I don't think I have colors here. Right, red. And actually, what? Just one minute. Well, it's dry, so why don't I just do this? I think you can see it well enough. The bullseye is in the center there. Now, let's say that I have darts that group this, a grouping of darts that are over here somewhere. So that grouping is not very close to the bullseye. So the percent difference is going to be very low because they're all very close to one another, right? They're almost very close to the same position. But the percent error is going to be high because they're very far away from the center, right? If I did something like this, well, the percent error is very low because I'm very close to the bullseye, but the percent difference is also very low because there's still basically percent difference measures grouping, how close the data is to the different data data points are to one another. If they're very close to one another, then the percent difference is going to be small and the grouping is going to be high. They're very close. And then, I can just play around with this, right? If I had something like this, the bullseye is here. So maybe the data spreads out like something like this. Well, that's both inaccurate and, it basically, and we can define, I'll do this later, we can define terms like precision and accuracy. Accuracy has to do with error, and precision is percent difference. So basically, they're all spread out, and the grouping is very low, so because they're not close to one another. So the percent difference is going to be very high because they're all over the place, and also the accuracy is also very low because they're not near the bullseye. So not accurate and not precise. This guy is precise. Precision measures grouping again, and precision measures grouping, and accuracy measures error. So this is precise because the objects are close, but it's not very accurate because it's away from the bullseye. This is both precise and accurate. Precise because the grouping is low, the objects are very close to one another, and accurate because it's very close to the bullseye. Yeah. So again, yeah, error analysis. Sometimes people will put this as step 6 and 7, but I kind of like wrap the error analysis under the calculation of percent error, percent difference under analysis. Yeah, and so then so I'm kind of running out of space here, but just a couple more steps for the scientific method. So hypothesis, experimentation, data collection, analysis. Now, we can wrap it up with conclusion. So what happens is after performing the experiment, we can conclude whether or not once we analyze the data, did the experiment validate our hypothesis? When we apply this process to various perspectives or various systems, do we get the same result over and over again, or are there differences? So essentially, there's a kind of, in the conclusion, I guess kind of with the analysis, there's kind of a recycling, right? So if when you're analyzing, after analyzing, if the analysis corroborates the hypothesis, then you move on and conclude some sort of general result, or maybe even make a theory if it continues to prove itself over and over again. If not, then you have to cycle back to and question everything that you've done before. Question the hypothesis. Do you need to change that? Or maybe the hypothesis is correct, but your experiment is off. Maybe you set up an experiment and you're not actually measuring the thing that you think you're measuring. Or maybe you did the experiment well, but your data is off. Like basically, if your analysis does not pass the test, or in the analysis, if your experiment does not pass the test, then you have to go back and question every aspect of what you just did. And you just keep doing that cyclically until in the analysis process, you'll feel that your hypothesis has been validated. And if so, then you make the conclusion and you report some sort of general result from your analysis, from your investigations. So, yeah, that's kind of the scientific method in a nutshell, so to speak. And yeah, any questions about that? Yeah, I kind of, that's probably almost half the chapter. They talked about that, and probably didn't do it as specifically as I did, but kind of just talked about different ways of applying science. Generally, what I do is take a little break at about an hour and a half in. So I'm going to take about a 15-minute break right now. Let's take a break. And when we come back, I'm going to finish up. We don't really need to go. I'm going to say something about I call it dimensional analysis, where you basically conversions, where you're converting things from one unit system to another, like how many seconds are in a year or something like that. fact, I might actually use that example as an illustration of dimensional analysis. They have an example in your first chapter there where they're converting something, but I'm going to give a kind of a process to it so that you can apply that process regardless of what the type of thing, regardless of what you're converting. Let's take a quick break. If you don't have any questions, take maybe 10, 15 minutes, and then we'll come back and I'll do that and then probably wrap up things and just give you some guidance about what we're going to, how to finish up the week in terms of your homework and quizzes and that sort of thing. Okay? All right. Take, so it's, hey, it's 9:40 right now. Let's come back in about 9:55. All right. Cool. We're back. Can you can everybody hear me okay? Excuse me. Okay, well, got a little break there. Let's talk about converting and something that I refer to as dimensional analysis. Oh. Okay. The dimensional analysis is a method by which we convert quantities from one unit system to another. Yeah. So I'm going to do a problem where we do something like usually, yeah. So there's, if you don't consider a leap year, there's 365 days in a year. So we can use dimensional analysis to determine how many seconds that is. So converting basically 365 years to seconds. Now, what we do is use conversion relationships to do that. Now, the overall point of view about this is actually what's happening. You all know that when you multiply a number by the value 1, then you don't change the value of that number. 2 times 1 is 2, so on and so forth. When you have a conversion relationship, it's a relationship that tells the amount of one quantity in one unit system as compared to another. For example, there are 12 inches in 1 foot. That's a conversion relationship. Let's take a look at that for a minute. So using the symbols, 1 foot, 1.0 feet equals 12.0 inches. Okay? This is an equality. Now, in algebra, when you perform a mathematical operation to one side of an equality, you have to do the same mathematical relationship to the other side of the equality. Otherwise, you change the value or you make errors or whatever. Now, this is just basic mathematical rules that I think you know. So let's do something where we divide this equality by 1 foot. So I'm going to divide the left side by 1 foot. But because I did that on that side, I have to do the same thing on the other side. So I divide this guy by 1 foot. Well, 1 foot divided by 1 foot is just 1. And over here, I have basically 12 inches. 12 inches per, well, the way we would say it is 12 inches per 1 foot or 12 inches per foot. But I'm going to keep it as a fractional term for illustration. So inches over 1 foot. Now, this ratio, 12 inches per 1 foot, is a quantity. But what this equality is now saying is that that value of that thing is equal to the value of 1. So if I then take that and use that ratio and multiply it by something, even though I would be changing its units, I wouldn't be changing the value of that thing because its value is 1. And even if I took the inverse, which is essentially just going back to the top and multiplying both sides by 12 inches, but I could just invert it here. Still, if I invert one side, I have to do the same thing to the other side. Well, I could make 1 into a fraction. How do you make any number into a fraction? By dividing by 1. So if I invert it, and the right side, I have 1.0 feet over 12 inches, I can just invert the other side, which is just 1 over 1 again, which is just 1. So the inverse is also equal to the value 1, even though its units are inverted. So again, if I take that ratio, 1 foot divided by 12 inches, and take that as a quantity and multiply it by something, even though the units would change, the value in that unit system would be the same, or the overall value is still 1. So I mentioned that just to let you know what we're about to do is we're going to be using conversion relationships, but we'll be using them in such a way that we'll be multiplying ratios of conversion relationships to these quantities. So, and we're not really changing the overall value. That we're just changing the unit. That's what conversion really is. And the formal name for that process is dimensional analysis. Okay, so the question is, how many seconds is in a year? Where a year is 365 days. So how many seconds in 1 year? Well, I start with that one conversion relationship, that 1 year. So I can start with 1 year. Usually, what you do is make that into a fraction by dividing by 1. So 1 year over 1. Now, I'm going to use various conversion relationships to convert that year to seconds. So I start with the conversion relationship that there's 365 days in 1 year. Now, again, I'm doing this for the purpose of illustration. You can probably take some shortcuts, whatever, if you know other conversion relationships or combining whatever. But I'm just going to do this for you just to illustrate. So you start with the thing that you're going to want to convert. I want to convert a year, so you turn it into a fraction by dividing by 1, so that I can now multiply by various conversion relationships in the form of the value 1. And we can kind of do this in our head. I could write down, 365 days in 1 year. Well, I guess I could do it over here and then go through that process of converting it to one, or I could just do it in my head, right? We could say that I'm multiplying this thing now by, so you always know that I've got two options. I can do 365 days in 1 year or 1 year in 365 days. Well, what I want to do is convert units from years to days. So if I were to write down 1 year is in, per 365 days, then that's not going to help me because when I multiply through, the units abide by the same mathematical rules as numbers. So when I multiply 1 times 1, I'm going to get 1. But when I multiply year times year, I get year squared. And I still got 365 days on the bottom. So that doesn't really help me in the way that I need. Because what I would like to do is cancel out years and convert basically years to days. So that's telling me that I really need to use the reciprocal of this conversion relationship, this conversion ratio. Because if I did that, and again, the value is still 1 either way, as I just illustrated here. But in terms of the units, I'm trying to get a specific unit system so that I can kind of convert down to the units that I need. And and again, this may be obvious to you, I don't know. But usually when people do conversions, they don't break it down like this. And so because you're usually converting things that you kind of already know how to do. But when you get more complex problems, I'm kind of a procedure person. Again, technique is what and we won't focus so much on technique here, but really, again, metacognition. How is it that I did something? How did I form that operation? Sometimes people are so talented that they kind of do things and they don't really know how they did it. You could see people talk about that all the time. Well, I don't know. It just kind of came to me or I did it. That's a talent. That's, just natural talent. At some point, talent runs out. I mean, meaning no matter how smart you are, there's going to be a problem out there that's so complex that even Einstein had to, with Einstein, it was general relativity and these things, right? So, and grand unification, trying to unify all the common forces. Knowing that we still haven't done that yet. Right? So, no matter how smart you are, it's the universe you're trying to figure out. Can outsmart the universe because it's the universe. So at some point, you're going to run up against a problem that's going to be very difficult to solve. So it's good to start with easy problems, figuring out process so that it kind of releases whatever talent you have, right? No matter how talented you are, if you understand how you are thinking, then it helps you to, I think, release that talent even more. So anyway, so let's get back to this. So I'm going to flip it around. So I'm going to go 365 days in 1 year. Now, when I perform the operation, I can clearly see that 1 times 1 is going to be 365. One is in the denominator is 1, but the units cancel. I've got years in the denominator here, years in the numerator here, so they cancel out, and I get whatever that number is going to be. We can see it's just going to be 365 because the algebra is pretty easy. But whatever that number would be, the units is going to be days. So I basically converted 1 year to days. And again, it just kind of mimics the conversion relationship. 1 year equals 365 days, but whatever. So now I'm going to go from days to, I guess, hours. So that conversion relationship is that there are 24 hours in 1 day, right? And I want to cancel out days. So should I use 24 hours in 1 day, or should I use 1 day for 24 hours? Well, if I have days in the numerator here, then in my conversion relationship, I want days in the denominator. So I'm going to write that down as 24 hours in 1 day. So there I can clearly see that days will cancel and I'm left with hours. Whatever that number is, and I can do the algebra in the end. I like to kind of do it all up before I do all the, the numbers. Yeah. And so now we want to go from hours. Well, you could go from hours to minutes and then minutes to seconds. But you could just jump from hours to, physicists do this a lot because it's something that we remember, because there's 60 minutes in an hour, but there's 60 seconds in a minute. So 60 times 60 is 3,600. So you could just use the conversion relationship that there are 3,600 seconds in 1 hour. And that would get it to us. So again, 3,600 seconds an hour, or 1 hour and per 3,600 seconds. Well, I need to cancel hours. So hours needs to be in the denominator of my conversion relationship. And what I would write then is 3,600 seconds per 1 hour. And in the end, hour cancels. So I start off with years. And if you go through and multiply, the only units that are left is seconds. So when I multiply all these numbers out, I know that it will be in units of seconds. So if we multiply that out, we got 365. I mentioned before, I don't have numbers like that, so I can't multiply that out in my head. Some people can. And we get 31 million. So 31,536,000 seconds in 1 year. So 1 year is equal to 31,536,000 seconds. Now, there is an issue. We won't talk about that so much here, I guess. Well, I will just leave it at that. But there's something called significant digits that when you get to higher order science classes, and Caitlin, I think you're the engineer, you're going to have to deal with this at some point. Significant digits. And technically, if I started with just 1 year or 1.0 year, then I only have 2 significant digits. So it really would be 1.0. If I started with that, then my final answer can only be as significant, we say in science, as the significance of my original values that I'm dealing with. So since that's technically 2 significant digits, I would probably be technically correct, scientifically correct, to round this off to 2 significant digits as an approximation. So you would say something like 32 million seconds, approximately 32 million seconds. Okay. Because rounding, and by the way, let's do the rounding thing. How do you round something? Well, if I have the number 6 point, let's do this, rounding. I think this is also maybe a bit of a review. But if you have a number like 6.5, that's 2 significant digits. If I want to round it up to the tens place, to the ones place, so this is ones, this is tenths. If I want to round it up to the ones place, you look to the number to the right of the decimal, or to the right, and if it's less than or equal to 5, then if it's greater than or equal to 5, then you drop that number, make it a 0, and then round this up to the number to the left up 1 digit. So that would round up to approximately 7.0. However, if this were 6.4, the number to the right of 6 being less than 5, then you drop that number and don't round the number up. So 6.4 rounds to approximately 6.0. And it doesn't matter if there's a decimal or not. If I had the number 54 or 450, that rounds to, again, if you want to round it to the, so this is ones, tens, hundreds. If you want to round it to the hundreds place, you look to the digit to the right. If it's less than 5, you drop it, place it with a 0, and then just round the other number up to 60. basically the next tenth place up. So 54, or the next 10th place up is 60. So drop that number around that. So this would be approximately 600. But if it were 57, 570, and that if you're rounding it to the 100th place, then it rounds to 800, because you go to the right of the 100th place, which is the 10th place. That's a 7. It's 5 or greater. So you make it 0 and then round you make it what do you do? You make it 0 and then you round the number to the left up to the next 10th place. So this would round up to sorry, I'm in my head. You drop the thing and you keep that the same. Sorry. So if it's 5 or less, you make it 0 and then keep this the same number. So this rounds to 500. My bad. Kind of thing what I want to do. So this thing is 5 or greater. So the 10th place, so you make it 0 and then round it up to 600. Sorry about that. All right, so that's what I was doing here. I look here. I'm going to round this up to the millions place. So this is the 10th of a millions place. This is a millions. This is 100,000, 10,000, 1,000, 1,000. Hundreds, tens, ones. So you look at the millions place, look to the right of that, and that's 5 or greater. So I drop that. Everything else beyond that is 0, goes to 0. And then the number to the left goes up to the next 10th place. And so this is round to 3,200. All those round. So that's rounding. And that's dimensional analysis. How much of you was that a review, or have you seen that before? Done that? Anybody? Caitlin, have you done that? Or you done that before? Yeah, awesome. Okay, good. Well, you know what? Would that be the final conclusion to that problem? 365 days, 24 hours, and basic algebra as you break it down. Yeah, I would say that would be the final answer. Would be it. Well, I don't think I'm going to have you all do. I don't think this book focuses on significant digits that much. That was, yeah. I had a feeling that you had done rounding before, so that's why I kind of threw that in there. But I think probably they would just let you stop here. Yeah. I've read through most of the book, and I don't remember it going into significant digits. In fact, they actually do a problem like this on page. Well, I've got it. Yeah, on. I don't think they rounded it. Oh, that's in chapter 2, actually. No, it's right here. Yeah, they don't. Yeah, actually, let me show you. I think I could probably share my screen. So, yes. So go to the book. I might have to come back out. I don't know if it goes to. Oh yeah, good. All right, chapter 1. What page is this? Page 12. I give them the page numbers. Page. All right, here you go. So they just convert this, I don't know, it's like blood circulation rate or something like that. Or heart rate. So they're converting it to something. It looks like that's what they're doing. Yeah. So yeah, they don't do any. Talk about, see, there's 72 beats and then 144 start from 144. Yeah. So they don't do any kind of significant digits there or anything. So, but that's an example of what, they don't call it dimensional analysis, but that's what it is. That's what I call it. So you can look through that. I think you're good. It's really just a matter of making sure you understand how to do the conversions. What just happened? Okay. It's new to me. That's why I asked. Yeah. Okay. Awesome. Good. Good. Well, that's any questions about it? Any other questions, Julie? You okay? I think she's writing. And of course, you can always, a safe environment, so you can ask anything. Completely different language. Okay. Well, I appreciate you sharing that. That's good. It's good. And, it's an introductory course, so that's all. It's all good. It's all good. Awesome. As a future teacher, I want to try to, I hope I can model good teaching. All right. Yeah. So I think that's going to be it for today. You can use this time to just start in reading the chapter and then working through the homeworks and the quizzes. And the quizzes, they're really, really simple. I think no quiz is more than 7 to 10 questions, but it's really just to help guide you through the reading as you go through. Yes, Genevieve?
Yes, I would just like to confirm that the book on the web page, it has to be purchased, or will you be like uploading version of it?
So you're not really purchasing the book, you're purchasing access to the Wiley Plus. So because the homework, everything that we access is through that Wiley Plus system. So when you go to like the homework on your homework page within your syllabus, there's a set of problems that you access. But what you're actually doing is accessing those problems on the Wiley site. It's paired or integrated. So it doesn't look like you're going to a different website. It's staying within your Canvas, but it's actually integrated the Wiley Plus homework page into your website. So the only way that you'll be able to access that homework and do the problems is if you register. So
okay.
once you register, say again.
There's a fee to register.
Yeah, it's like I think the cheapest one is like 70. I think someone wrote it earlier. $79 for a semester.
Okay, thank you. Just because I was a little bit confused for that, but okay, that clarifies it. Thank you.
Yeah, and when you do register, it automatically gives you a digital copy of the book. So you're not really, because the book is actually much more expensive than that, I believe. In fact, I know it is a new version. So you just get basically a free digital version of the book when you register.
Okay,
all right.
Thank you.
Yep. Any other questions? Okay, well, thank you for coming to class. Got through the first day, and I hope you found it enjoyable. And oh yeah, there's a 2-week. Actually, kind of helps with the 8-week course. There is even more so for the 5-week one. But they always give you a 2-week grace period where you can use it for 2 weeks for free. So that helps a little bit.
Oh, that's great. And then also, but to do the homework in the future, we do need to have the access we need to have it open and accessible, right?
Yeah,
Okay.
that's correct. Yes, that 2 week grace period gives you full access to everything, but they do cut it off after 2 weeks. And yeah, so yeah. All right.
Yes, thank you very much.
Okay. Well, if you don't have any other questions or anything, that's dismissed. So when will we be getting the code for the lab? Oh, you should have already gotten it, but if not, he's mailing it this week, I guess. He said he was going to mail it last week, but you might check your inbox. His email address is his name is Ruben Venezuela. Let me see if I can find. I forgot his email. It's I have to check my email. Check real quick. Mm-hmm.
I have a question.
So
What days will
the
the
lab
be on?
doesn't meet.
Okay.
I'll be publishing that the shell for it, but there's no class scheduled meetings for the lab, and we
Okay.
basically be doing just one per week, and that's it. Yeah, one lab per week with the through the Wiley Plus.
Okay, thank you.
Villanueva, and his email address is Villanueva. Yeah, so maybe look for this email. It's either in your you might want to look in your deleted message, or not deleted, but spam mail or something like that. And he should be sending you some sort of yeah, he sends the codes to you. Or he might do it as a class. Yeah, I don't know. He's going to email it. But maybe that hasn't gone out yet. All right. Yeah. So is that anything else? Haven't got it yet. Okay. All right. Cool. Well, we'll check in on Wednesday. Still, we generally sometimes I don't generally. Oftentimes well, for the 16 weeks, I don't usually do a lab on the first week because we're 8 weeks. We probably will assign them. I'll give you plenty of time. These things they're more like lab exercises. They only usually take about an hour and a half or so once you get familiar with the software to do them, sometimes even less than that to actually do the lab, but then maybe a little longer to answer the question. All right. Yeah. Well, yeah, anything else? All right. Well, I enjoyed you the first day. I think this was a great start, and I look forward to I'll see you on Wednesday.
Okay, you have a good day.
Thank you, Professor.
Okay. Bye-bye.